Welcome. You have nothing to do right now, nowhere to be, nothing to figure out. Let your body settle into wherever you are resting, and allow your breath to slow and deepen. Tonight, we are going to drift together through the long, slow story of the universe itself, a journey measured not in days or years, but in spans of time so vast and serene, they dissolve all worry. Simply let the words wash over you and rest. The universe is currently about 13.8 billion years old. That number is almost too large to hold in the mind, and perhaps that is part of its comfort. 13.8 billion years of stars being born and fading, of galaxies slowly wheeling through the dark. And yet here we are, a brief and luminous moment somewhere near the middle of it all. The cosmos has been quietly unfolding for an almost unimaginable span, and it will continue long after this gentle night has passed. The observable universe spans roughly 93 billion light-years in diameter. That is the sphere of space whose light has had time to reach us since the beginning, a bubble of visibility inside something far larger and unknowable. Every direction you look, galaxies stretch outward to a horizon defined not by walls but by time itself. The light entering your eyes on a clear night left those distant suns long before our earliest ancestors walked the earth. There is something deeply restful in knowing we are held inside something so boundlessly wide. The cosmos is expanding at an accelerating rate, driven by a mysterious force called dark energy. Not only is every distant galaxy moving away from us, but that movement is speeding up, slowly and steadily, like a breath being exhaled with no intention of returning. The universe is not collapsing inward or holding still. It is opening, widening, growing more spacious with every passing moment. There is something almost meditative in that image, a cosmos that simply keeps expanding, unhurried and immense. Dark energy makes up approximately 68% of the total energy content of the universe. More than two-thirds of everything that exists is this invisible, pervasive presence woven into the very fabric of space. We cannot see it or touch it, yet it shapes the destiny of all things. Scientists are still working to understand its true nature, but they know it is there, steady and patient, the quiet majority of the cosmos, holding the universe open like two hands gently pressing outward. Dark matter comprises about 27% of the universe's total mass and energy. It does not emit light or absorb it, yet its gravity shapes the scaffolding on which all galaxies are built. Great invisible halos of dark matter surround every galaxy, holding stars in their orbits like a silent, unseen hand. We have never directly detected a single dark matter particle, and yet without it, the galaxies we know and love would never have formed at all. It is a profound reminder that most of reality lies just beyond our sight. Ordinary matter, the stuff of stars, planets, oceans, and every living thing, accounts for only about 5% of everything that exists. All the mountains and moons, all the books and breathing creatures, every atom ever measured or named, together make up just one small fraction of the whole. It is a humbling thought, and also a strangely freeing one. The universe is mostly something we have not yet learned to name. We are a small and wondrous flourish in a much larger, quieter composition. The Hubble constant measures how fast the universe is expanding today. Named for the astronomer Edwin Hubble, it describes the rate at which galaxies drift apart as space itself stretches between them. Astronomers measure it in kilometers per second, per megaparsec, a way of saying how much faster a galaxy moves away for every additional unit of distance. There is a gentle tension in current measurements, with different methods giving slightly different answers, and scientists believe that tension may one day point toward new physics entirely. Distant galaxies are receding from us faster than the speed of light, simply due to the expansion of space. This is not a violation of any law. Nothing is moving through space faster than light. Rather, the space between us and those far galaxies is itself growing so quickly that the distance increases beyond what light can ever bridge. Those galaxies are not gone, but they are forever beyond our reach, drifting past a horizon we can never cross. There is something tender in that, a farewell written in the geometry of space itself. The cosmic microwave background radiation is the afterglow of the Big Bang, the oldest light in the universe. It fills all of space in every direction, a faint, even warmth left over from a time when the cosmos was a dense, blazing sea of energy. Today, it has cooled to just about 2.7 degrees above absolute zero, barely a whisper above nothing. If you could tune a radio to the right frequency and listen, you would hear a soft, steady hiss, the universe still murmuring to itself from its very first moments. Let your body settle now, just a little more. Let the weight of the day dissolve into the surface beneath you. There is nothing to hold on to, nothing to figure out. Your breath moves slowly, in and out, like a tide finding its own rhythm. The mind can wander wherever it wishes, or it can simply rest here, in this still and unhurried moment. You are safe and warm, and there is nowhere else you need to be. The Andromeda Galaxy is currently on a collision course with the Milky Way. Right now, as you rest, that great spiral of stars is drifting toward us through the dark, slowly, steadily, carried by gravity's patient pull. It is already the most distant thing visible to the unaided eye on a clear night, a faint smear of light more than 2 million light-years away. And yet it draws closer, year by year, in a long, unhurried approach that has been unfolding for billions of years. Andromeda and the Milky Way will begin to merge in about 4.5 billion years. That span of time is so immense it dissolves into something almost dreamlike, longer than the Earth has existed, longer than the Sun has burned. The two galaxies will drift toward each other across the cosmos, drawn together by the same quiet force that holds you to the ground. When they finally meet, it will be the beginning of something entirely new. The merger of Andromeda and the Milky Way will form a new elliptical galaxy, where two graceful spirals once turned slowly through space. A single, rounder, more diffuse structure will emerge, its stars redistributed into gentle, sweeping orbits. Elliptical galaxies have a kind of quiet grandeur, less structured than spirals, but luminous and vast. The merger is not destruction, but transformation, two things becoming something neither was before. Astronomers have given the future merged galaxy a gentle name, Milkomeda. It is a small, tender thing, a blending of two names into one, the way two rivers meet and become something larger. The name carries a kind of affection, a way of reaching across unimaginable time and acknowledging what is coming. Scientists use it almost fondly, as though they are already acquainted with this galaxy that will not exist for billions of years. The collision will not destroy individual stars, because the space between them is so extraordinarily vast. Even within a galaxy, stars are separated by distances so immense that two galaxies can pass through each other and barely a single star will collide. The night sky, as seen from a planet inside either galaxy, would grow slowly more crowded, more luminous, but the stars themselves would drift past one another like snowflakes falling through an open field. The light entering your eyes tonight left some of those distant stars before our earliest ancestors ever walked the Earth. Our Sun will exhaust its hydrogen fuel in about 5 billion years. For most of its life, the Sun has been a steady, reliable furnace, fusing hydrogen into helium at its core, releasing the warmth that makes life possible. But like all things, it carries within it a quiet limit. Over billions of years, that hydrogen will thin and diminish, and the Sun will begin a long, slow change. It has already burned for about 4.6 billion years, and roughly that much time remains. As the Sun runs low on hydrogen, it will expand into a red giant, The core will contract and heat, and the outer layers will swell outward in a slow, majestic bloom, the sun growing hundreds of times its current size, its surface cooling and shifting from yellow-white to a deep, burnished red. It will be a transformation measured in millions of years, unhurried and immense. The inner solar system will be remade entirely, bathed in a ruddy, diffuse warmth unlike anything we know today. The expanding sun will likely engulf Mercury and Venus as it swells into its red giant phase. Those two inner worlds, which have orbited steadily for billions of years, will be drawn into the sun's growing envelope and dissolved. It will happen so gradually that there is no single moment of ending, just a slow immersion, the planet spiraling inward through increasingly dense stellar material until they are simply gone, absorbed back into the star that once lit them. Earth's oceans will evaporate long before the sun becomes a red giant, as the sun brightens steadily over the next billion years. Even now, the sun grows very slightly more luminous with each passing age. Over hundreds of millions of years, that added warmth will push Earth's climate past a threshold from which it cannot return. The oceans will rise into the atmosphere as vapor, and the skies will thicken with clouds of water, trapping heat until the surface grows too warm for liquid seas. The blue world we know will become something else entirely: dry, bright, and still. When the sun's red giant phase draws toward its close, it will gently release its outer layers into space, forming a luminous cloud called a planetary nebula. Over tens of thousands of years, those expelled shells of gas will drift outward in slow, expanding rings, glowing with soft colors as the radiation from the cooling core illuminates them from within. Blues and greens and rose-tinted veils of gas, spreading silently across the surrounding darkness. It is one of the most serene endings in the cosmos, a star quietly breathing itself out into the universe. Let your body settle a little deeper now. There is nowhere to be, nothing to hold on to. Let your shoulders release, let your jaw soften, let your hands rest open and easy. With each slow breath out, you can feel the thoughts of the day growing lighter, drifting further away. You are safe, you are still, and you are being gently carried toward rest. Let the vast, unhurried story of the universe wash over you like a warm and distant tide. After shedding its outer layers, the sun's dense core will remain, a white dwarf, roughly the size of Earth, but carrying more than half the sun's mass. Compressed into that small, dense sphere, the remaining material will glow with a pale, steady light, not from fusion, but from the heat stored within it over billions of years. It will be a quiet, diminished thing compared to the star it once was, but still luminous, still warm. A last ember of the sun floating in the dark. Over trillions upon trillions of years, white dwarfs slowly release their stored heat into the surrounding darkness, cooling and dimming with extraordinary patience. Eventually, theory tells us, they will fade entirely, becoming cold, dark spheres of crystallized matter called black dwarfs, invisible against the night. The cooling is so gradual that it cannot be measured in any human span of time. It is a dimming so slow it resembles stillness, a long exhale stretched across more time than the universe has yet existed. Here is something quietly remarkable. Not a single black dwarf exists anywhere in the universe today. The cosmos, at nearly 14 billion years old, is simply too young. Even the oldest white dwarfs, those born from the very first generation of stars, have barely begun to cool. The timescales required to produce a true black dwarf stretch far beyond anything the universe has yet experienced. Every white dwarf out there is still glowing, still warm, still early in its long, unhurried fade toward darkness. Stars like our sun are not the longest-lived inhabitants of the cosmos. Within roughly 100 billion years, about 7 times the current age of the universe, the last of the sun-like stars will have exhausted their fuel and faded away. One by one, across billions of years, they will swell, shed their layers, and leave behind white dwarfs drifting in the dark. The galaxy will grow quieter with each one that goes. The familiar stars of the night sky belong to a chapter that is already, on cosmic timescales, more than halfway through. Red dwarf stars are the most numerous stars in the universe, and they burn their fuel with extraordinary economy. Where a star like the Sun consumes hydrogen at a prodigious rate, a red dwarf sips it with great care, its interior slowly and steadily converting hydrogen to helium over timescales almost impossible to comprehend. They are small, cool, and dim, glowing a deep, ruddy orange rather than the bright white yellow of the Sun. Unassuming and unhurried, they will outlast nearly everything else in the stellar universe. The very smallest red dwarfs can sustain their gentle fusion for up to 10 trillion years, nearly 1,000 times the current age of the universe. A single one of these modest stars, barely large enough to ignite, will still be burning long after every sun-like star has come and gone. If any world orbits such a star in the right zone of warmth, it could be bathed in that faint reddish light for an almost unimaginable span. The light entering your eyes tonight left the Sun just 8 minutes ago, but these small stars will still be glowing when that span of 8 minutes is less than a memory. Even as stars continue to shine across these vast timescales, the raw material for making new ones will slowly run out. Galaxies are born with great reservoirs of gas, the clouds from which stars condense and ignite. But with each new star formed, some of that gas is locked away or dispersed. Over billions of years, the rate of new star formation will taper, gently and steadily, like a fire that is not extinguished but simply runs short of fuel. The universe will not suddenly go dark. It will simply stop refreshing its lights. By roughly 100 trillion years from now, a number so large it dissolves quietly into abstraction, the era of star formation will have effectively come to a close. The last stellar nurseries will have grown cold and still. No new suns will ignite to replace those that have faded. The universe will still contain its aging red dwarfs, glowing on in the dark, but the great creative epoch of stellar birth will be over. It is not an ending that happens all at once. It is more like the last light leaving a room as the sun sets very, very slowly outside. When the last stars have finally dimmed, the universe will cross a quiet threshold into what scientists call the degenerate era. There is no dramatic announcement, no sudden shift, only a gradual deepening of the dark. The fires that warmed the cosmos for unimaginable ages simply cease to be renewed. What remains is a universe of remnants, of cooling embers, of matter that once blazed and now rests. The degenerate era will last far longer than the age of stars ever did. The degenerate era is shaped by 3 kinds of objects: brown dwarfs, white dwarfs, and neutron stars. These are the quiet inheritors of the stellar age, not burning brightly, but persisting with extraordinary patience. Brown dwarfs glow faintly with residual warmth. White dwarfs cool with unhurried grace. Neutron stars spin slowly in the dark, ancient, and dense. Together they populate a universe that is not empty, but hushed, a vast, dim archive of everything that once shone. Let your body settle now, just a little more deeply into wherever you are resting. There is nothing to hold on to, nothing to work out. Let your shoulders soften. Let your breath find its own unhurried pace, in and out, slow and even. Each thought that drifts through your mind can simply pass, like a cloud moving across a still sky. You do not need to follow it. You are here, and you are safe, and there is nothing at all that needs doing now. Just rest. Round dwarfs are objects that came so close to becoming stars, but never quite crossed the threshold. They gathered from clouds of gas, just as true stars do, and they even glow with a faint warmth from the heat of their formation. But they are too small, not massive enough for their cores to sustain the hydrogen fusion that defines a true star. They are sometimes called failed stars, though that phrase carries more judgment than they deserve. They are simply a different, quieter kind of world. Neutron stars are among the most extraordinary objects in the universe, born from the violence of a massive stellar explosion, and yet arriving at a state of profound stillness. When a very large star exhausts its fuel, its core collapses with tremendous force, and what remains is an object only about 20 kilometers across, roughly the width of a city, yet containing more mass than the Sun. Matter inside a neutron star is packed so tightly that a single teaspoon of it would weigh billions of tons on Earth. Some neutron stars spin with breathtaking speed and emit sweeping beams of electromagnetic radiation from their magnetic poles. These are called pulsars. As the star rotates, the beam sweeps across space like the beam of a distant lighthouse, steady and rhythmic. Some pulsars rotate hundreds of times per second, their timing so precise that astronomers once used them as the most accurate clocks in the known universe. Even in the deep quiet of the degenerate era, some of these ancient lighthouses may still be turning. Black holes form when the most massive stars reach the end of their lives and their cores collapse under the weight of their own gravity, a weight so immense that nothing, not even light, can escape the resulting pull. The outer layers of the star are expelled in a tremendous explosion, while the core falls inward past any known boundary of density. What remains is a region of space-time so deeply curved that it becomes, in a sense, a hole in the fabric of the universe itself. They are not empty, they are full, beyond measure. The black holes that form from individual stars, known as stellar mass black holes, are typically between 3 and 20 times the mass of the Sun. They are compact and dark, invisible against the blackness of space unless matter is falling into them and glowing as it spirals inward. Scattered across every galaxy in the universe, there may be hundreds of millions of these objects drifting silently through the dark. Each one is a sealed record of a star that once burned, a kind of permanent, lightless memorial. At the centers of nearly all large galaxies, including our own, there lurk black holes of an entirely different scale, supermassive black holes containing millions or even billions of times the mass of the Sun. How they grew so immense is still something scientists are working to understand, but their presence shapes the entire galaxy around them. Stars orbit them from safe distances, their paths curving gently around a center of gravity too deep to fathom. Even in stillness, these vast objects anchor the structure of the cosmos. The supermassive black hole at the center of our own Milky Way is known as Sagittarius, a star. It sits roughly 26,000 light-years from Earth, hidden behind vast clouds of gas and dust. In the year 2022, astronomers released the first direct image of it, a glowing ring of warm orange light surrounding a central shadow. It had been there all along, patient and immense, at the very heart of the galaxy we call home. The light in that image traveled 26,000 years to reach us. Sagittarius, a star, the great black hole at the heart of our galaxy, holds within it the mass of about 4 million suns. 4 million. A number so vast it dissolves into abstraction, like trying to count every grain of sand on a long, unhurried shore. Yet it sits there, serene and motionless at the galaxy's center, neither consuming nor retreating, simply present. All the stars in the Milky Way wheel slowly around it across hundreds of millions of years, as if in a vast, unhurried dance. It is the still point at the center of everything we call home. And yet, Sagittarius, a star, for all its enormity, is not the largest black hole we know of. Some black holes carry masses billions of times greater than the Sun, objects so immense they strain the imagination into silence. The black hole at the heart of a distant galaxy, known to astronomers as Messier 87, for example, holds the mass of nearly 6.5 billion suns within it. These are the true titans of the cosmos, ancient and unhurried, having grown over billions of years by drawing in whatever drifted close. They are the deepest stillnesses the universe has ever made. When massive objects collide, black holes, neutron stars, they do not do so in silence. They send out ripples through the very fabric of space-time itself, distortions that travel outward in every direction at the speed of light. These are gravitational waves, and they pass through everything, planets, stars, and even you, stretching and compressing space by amounts so tiny they are almost beyond measure. Scientists first detected them directly in the year 2015, and the signal they received had traveled over 1 billion light-years to arrive. The universe had been whispering this way all along, and we had only just learned to listen. There is nothing you need to hold on to right now. Let your shoulders settle a little lower, and feel the weight of your body resting fully where you lie. Each breath comes and goes on its own, slow and easy, like a tide that knows exactly what it is doing. The thoughts that drifted through your day are already becoming distant, faint, and unimportant, like stars at the edge of vision. You are here, you are still, and the universe is vast and unhurried all around you. There is only rest. Many stars in the universe do not travel alone. They orbit one another in pairs called binary systems, two suns bound together by gravity in a slow, eternal waltz. But over immense spans of time, these pairs are not truly eternal. As they orbit, they lose tiny amounts of energy by radiating gravitational waves outward into space, and with each orbit, they draw ever so slightly closer together. Across millions or billions of years, this gentle drain of energy causes them to spiral inward, growing nearer and nearer, until, at last, they meet. It is one of the most gradual embraces in the universe. When two neutron stars finally spiral together and collide, the result is an event of extraordinary richness called a kilonova. In the furious heat and pressure of that collision, elements heavier than iron are forged, gold, platinum, and silver among them. The gold in a ring, the silver in a spoon, the platinum in a laboratory instrument. All of it was born in the fire of colliding neutron stars, scattered across space and eventually gathered into planets and people. We carry the remnants of those ancient blazing meetings within us. Every gleam of gold is a memory of something magnificent. Over time scales almost too long to hold in the mind, the gravitational interactions between stars will gradually reshape every galaxy in the universe. Stars passing near one another exchange tiny amounts of momentum, and over trillions upon trillions of years, these countless small nudges add up. Most stars will eventually be flung outward, drifting away from their galaxies entirely into the vast, featureless dark between them. A small number will fall inward toward the central black hole. The galaxies we know, rich, luminous, full of light, will slowly dissolve like salt in a very deep and very patient sea. While individual galaxies will slowly unravel, there are structures in the universe bound together so strongly that they will endure far longer galaxy clusters. These are the largest gravitationally bound objects in the cosmos, collections of hundreds or even thousands of galaxies, all held together within a shared web of dark matter spanning millions of light years. The Virgo cluster, the Coma cluster, the Perseus cluster, each one a community of galaxies drifting together through the deep. They are the great anchored islands of the universe, vast and slow and enduring. As the universe continues to expand, Galaxy clusters will grow more and more isolated from one another, separated by distances so immense that even light from one cluster will never reach another. But within each cluster, the gravitational bond will hold. The galaxies inside will remain together, orbiting their shared center of mass across unimaginable stretches of time, even as the rest of the universe recedes beyond any horizon. Each cluster becomes its own small, sealed universe, a quiet gathering of ancient light, adrift in an ever-emptier expanse. And so the stars will burn on, long after the Milky Way has merged and reshaped itself, long after our sun has cooled to a cinder. The red dwarfs, those small, unhurried stars that burn their fuel so slowly and so carefully, will be the last lights in the universe. But even they are not forever. In roughly 10 to the power of 14 years, a 1 followed by 14 zeros, a number so enormous it has no comparison in human experience, the very last red dwarf will exhaust its fuel and fade. The universe's age of stars will draw to a close, as all things do, in stillness and in dark. As the last red dwarfs fade, the universe will grow increasingly dark, star by star, until almost no light remains. This is not a sudden event, it is a slow, unhurried dimming, spread across timescales so vast that each individual extinction would go unnoticed. One by one, across every galaxy cluster still bound together, the ancient fires will go out. The cosmos will settle into a deep, pervasive darkness, the way a forest grows still and shadowed long after the last lantern has been carried away. There is a theoretical process that scientists call proton decay, and if it exists, it means that even the matter left behind in that long darkness may not last forever. Protons are among the most fundamental building blocks of atoms, and atoms are the substance of everything we have ever touched or seen. But certain theories in physics suggest that protons may not be truly permanent, that given enough time, even they may quietly dissolve, releasing their stored energy in a final, unhurried unraveling of ordinary matter itself. It is worth noting, gently, that the standard model of particle physics, our most thoroughly tested and carefully built framework for understanding matter, does not predict proton decay. Within its equations, protons are stable. They have no mechanism to dissolve. The standard model has passed every experimental test physicists have devised, and by its accounting, a proton left undisturbed would remain a proton indefinitely. This is not a flaw in the theory. It is simply where the theory, for now, quietly stops. Beyond the standard model, there are broader theoretical frameworks known as grand unified theories, which attempt to weave together the fundamental forces of nature into a single description. Several of these theories do predict that protons can decay, but only after an extraordinarily long time. The half-life of a proton, according to some of these models, may be 10 to the 34 years or more, a number so immense that writing it out as a word would take longer than any star has ever burned. It is a time scale that makes the current age of the universe feel like the first quiet breath of a very long night. There is nothing you need to hold on to right now. Let your thoughts drift wherever they wish, like leaves carried by a slow and gentle current. Feel the weight of your body settling, your shoulders, your hands, the back of your head resting softly where it lies. Each breath you take is slower than the last, and that is exactly right. You are already moving toward sleep. Let the vast, unhurried darkness of the universe be a comfort. Nothing is rushing, nothing is urgent, and all of time stretches out around you, wide and still and endlessly patient. If proton decay is real, then its consequences reach all the way down to the very foundation of physical existence. Every atomic nucleus is built from protons and neutrons, and if protons can dissolve, then nuclei will dissolve with them. Atoms themselves will come apart. The matter that forms planets, moons, the remnant husks of ancient stars, all of it would slowly, imperceptibly unravel, releasing energy in tiny increments across inconceivable stretches of time. The universe would not shatter. It would simply, and very slowly, let go. To search for proton decay here on Earth, physicists built remarkable instruments, among them a detector in Japan called Super Kamiokande, a vast underground tank filled with 50,000 tons of ultra-pure water, watched over by thousands of light sensors waiting for the faintest possible flash. For decades, this extraordinary device has listened in the deep quiet beneath a mountain, watching for a proton to dissolve. So far, none has been observed. The protons remain, the silence continues, and the search goes on, patient and unhurried, in the dark. If protons do not decay, if they are truly stable, as the Standard Model suggests, then matter will persist far longer than any decay scenario would allow. White dwarfs and neutron stars, those dense and cooling remnants of stellar lives, would endure across timescales that dwarf even the age of star formation. They would not shine. They would not warm anything, but they would remain solid, composed, patient, like stones resting at the bottom of a river so deep and so still that no current has ever disturbed them. Even in a universe where protons hold together, physics allows for something stranger still. Quantum mechanics tells us that particles do not occupy fixed positions, they exist within a range of probabilities, and over long enough timescales, matter can shift into lower energy configurations through a process called quantum tunneling. Scientists believe that a white dwarf left undisturbed for roughly 10 to the 25 years, a number almost beyond all reckoning, might slowly tunnel its way into a sphere of iron, the most stable arrangement of nuclear matter. Grain by grain, over an eternity, the remnant of a star would quietly reorganize itself. Neutron stars, too, carry within them the quiet possibility of transformation across unimaginable time. Scientists theorize that even without a companion to steal matter from, a neutron star might eventually collapse into a black hole, not through any dramatic event, but through the same patient process of quantum tunneling. The probability of such a collapse in any given moment is extraordinarily small, but time, in this era of the universe, is the one thing available in boundless supply. And so even these dense, enduring remnants may one day cross a threshold, folding inward in absolute silence, becoming something else entirely. Stephen Hawking proposed that black holes slowly radiate energy through a quantum process. For much of the 20th century, black holes were thought to be perfectly silent, consuming everything, releasing nothing. But Hawking, working at the intersection of quantum theory and gravity, arrived at a remarkable and counterintuitive conclusion that black holes are not entirely dark. They glow, ever so faintly, with a whisper of energy that leaks outward into the surrounding void. It was one of the most surprising and beautiful ideas in all of modern physics, a discovery that arrived not through observation, but through the quiet discipline of pure thought. This process is called Hawking radiation, and it causes black holes to slowly lose mass over time. The name honors the physicist who first described it, Stephen Hawking, and it represents a bridge between two great pillars of science that have never been fully reconciled. Hawking radiation is extraordinarily faint. For a black hole of stellar mass, the temperature of this radiation is far colder than the cosmic microwave background, colder than anything we could measure with any instrument we possess. And yet it is real, and it means that black holes, those seemingly eternal engines of gravity, are in fact impermanent. They too will pass. Hawking radiation arises from quantum effects near the event horizon, where virtual particle pairs are separated before they can recombine. In the quantum world, empty space is never truly empty. Pairs of particles and their antiparticles flicker in and out of existence constantly, arising from borrowed energy and vanishing almost instantly. Near the edge of a black hole, however, one member of such a pair may fall inward, while the other escapes outward into space. The escaping particle carries energy away from the black hole, and the black hole itself pays the cost. It is a slow and silent transaction, conducted at the very boundary between existence and oblivion. A stellar mass black hole would take about 10 to the 67 years to fully evaporate through Hawking radiation. Written out, that number is a 1 followed by 67 zeros, a span of time so immense it renders all previous timescales we have visited tonight almost trivial by comparison. The entire current age of the universe, 13.8 billion years, would not even register as a breath against such a duration. And yet Hawking radiation, patient and relentless, would work its way through even these vast reservoirs of mass, one faint particle at a time, across an ocean of time without any shore in sight. A supermassive black hole of 1 billion solar masses would take about 10 to the 96 years to evaporate. These are the giants that anchor the hearts of galaxies, objects of such extraordinary mass that even the universe's current age is less than a single heartbeat of their lifespan. 10 to the 96 years is a number that no human language was designed to hold. It is longer than the time required for quantum tunneling to reshape white dwarfs, longer than nearly any process we have yet encountered in this long journey through deep time. The light entering your eyes tonight left its source millions of years ago, and yet even that vast distance is nothing beside the patience of a supermassive black hole slowly dissolving into the dark. There is nothing you need to hold on to right now. No thought requires your attention. No task is waiting. You can simply rest here, carried gently along by the slow current of these vast and distant ideas so large and so unhurried that they dissolve the small concerns of the day, the way morning light dissolves a dream. Let your body settle a little more deeply into wherever you are resting. Feel the weight of your limbs, the rise and fall of your breath, the warmth of the space around you. You are safe. You are still. Let your thoughts grow quieter, like ripples on a pond that has stopped being disturbed. There is nothing to figure out tonight, only rest. As a black hole shrinks through Hawking radiation, the process gradually intensifies. There is an elegant and almost paradoxical quality to this. The smaller a black hole becomes, the hotter its Hawking radiation grows, and the faster it loses mass. It is as though the long, slow patience of evaporation gives way, near the end, to something swifter, the way a candle burns most brightly in its final moments before the flame consumes the last of the wax. Over inconceivable timescales, the process is imperceptibly slow, but in the closing chapters of a black hole's existence, the pace quickens toward a final irreversible conclusion. In its final moments, a black hole releases a brief burst of high-energy particles. After an almost incomprehensible duration of slow, silent evaporation, the very last remnant of a black hole disappears in a sudden outpouring of energy, a flash in the dark, a last exhalation. Scientists believe this final burst would be unlike anything else in the universe, a concentrated release marking the complete dissolution of something that once held entire solar systems in its gravitational embrace. And then it is gone. Where there was once a black hole, a region of space from which nothing could escape, there is simply open space again, as though it had never been. The last black holes in the universe will eventually evaporate, leaving behind only radiation and the most fundamental of particles. By this era, unimaginably far into the future, the universe will have grown extraordinarily sparse. No stars, no planets, no galaxies as we would recognize them, only the ancient, cooling remnants of black holes completing their long dissolution. When the final one fades, something profound will have ended. The last concentrations of organized mass in the cosmos will be gone. What remains will be a diffuse, thinning sea of particles and radiation, spread across a space grown almost incomprehensibly vast through billions upon billions of years of expansion. After the last black hole evaporates, the universe enters what scientists call the dark era. It is a name that carries a certain stillness within it, not darkness as something threatening, but darkness as a kind of absolute quiet, a universe that has grown fully into its own silence. No light sources remain. No structure persists. The cosmos drifts onward in a state of near-perfect uniformity, expanding still, cooling still, thinning still, a vast and featureless expanse where the concept of a meaningful event has almost ceased to apply. And yet the universe continues. It does not end here. It simply becomes something far beyond what any of our words were made to describe. The dark era universe contains only the lightest and most fundamental of particles, photons, neutrinos, electrons, positrons, and other delicate remnants of what matter once was. All the grand architecture of the cosmos, the galaxies, the nebulae, the intricate webs of stars, has long since dissolved. What persists now is only the barest residue, a scattering of particles drifting through a space so enormous that the distance between any two of them defies comprehension. The universe has become, in the most literal sense, nearly nothing at all, and yet these faint traces carry on, witnesses to everything that ever was. Electrons and positrons, drifting alone through the dark era, will eventually find one another and annihilate, producing photons in a last, quiet exchange. When a particle of matter meets its antimatter twin, they do not collide violently, they simply cease, transforming entirely into light. Across the unimaginable span of the dark era, these brief wordless meetings will occur one by one, each one a tiny completion, a small closing of an account opened long ago at the dawn of the universe. With each annihilation, a little more matter dissolves into pure radiance, until no electrons or positrons remain, only the photons they left behind. The photons that filled the dark era will be stretched by the universe's continued expansion until their wavelengths grow enormously long. Light, as it travels through expanding space, is gently pulled apart, its waves lengthening, its energy diminishing, its color shifting from the visible into the infrared, then into the radio, and then into wavelengths so vast they have no name in any human language. These photons will not vanish, but they will become so dilute and so faint that the universe they inhabit will be, for all meaningful purposes, dark. The light that once illuminated stars and warmed planets will have stretched itself into near silence. The average temperature of the dark era universe will approach absolute zero asymptotically, drawing ever nearer without ever quite arriving. This is one of the most serene images in all of science, a cooling that never fully completes, a slow descent toward stillness that continues without end. With every passing era, the universe grows fractionally colder, shedding the last remnants of thermal energy into its own vast interior. The curve of its cooling bends always downward, always toward that ultimate quietude, but like a horizon, it recedes as it is approached, forever almost there, forever not quite reached. Absolute zero is the theoretical temperature at which all thermal motion ceases, the deepest cold that physics allows. At this temperature, atoms would be entirely motionless, stripped of the last trembling vibrations that define warmth. Scientists believe that quantum mechanics prevents any real system from ever reaching absolute zero precisely. But the concept marks the ultimate boundary of cold, the floor beneath all floors, the silence beneath all silence. It is expressed as -273.15 degrees Celsius, a number that carries within it the idea of a universe, finally, completely at rest. The concept of heat death describes a universe that has reached maximum entropy, a state in which no usable energy remains anywhere. It is not death in any dramatic sense, but rather a final, complete equilibrium, a universe so thoroughly mixed and so uniformly spread that no difference exists anywhere from which work could be drawn. No warm region beside a cool one, no concentrated energy, beside an empty one, just an unbroken sameness, stretching in every direction across all of space. The universe does not end with a collapse or an explosion in this vision. It simply settles, like a lake on a windless morning, into absolute and total stillness. The light that once left a distant galaxy before our earliest ancestors walked the Earth will have long since faded into this vast, featureless calm. Let yourself settle a little more deeply now. There is nothing left to hold on to tonight. No task waiting, no thought that needs your attention. Simply feel the weight of your body resting where it is, easy and unhurried. Let your breathing find its own slow rhythm, each exhale a little longer, a little more complete. You are here, and you are safe. And the only thing asked of you right now is to let go, to soften, to drift, to allow sleep to come in its own quiet way. There is nowhere to be but here, and here is very still. Ludwig Boltzmann, a brilliant Austrian physicist of the 19th century, first developed the statistical mechanics framework that underlies our understanding of heat death. Working in an era when the atomic nature of matter was still debated, Boltzmann showed with extraordinary mathematical insight that the behavior of heat and energy could be understood through the collective motion of countless tiny particles. His ideas were not always welcomed in his time, but they laid the foundation for everything we now understand about entropy and the direction of time. In the long arc of science, his quiet, careful work became the lens through which we see the universe's deepest future. Entropy is a measure of disorder, and the second law of thermodynamics tells us that in any closed system, entropy always increases or stays the same. It never spontaneously decreases. This is one of the most fundamental and far-reaching laws in all of science. It is why a drop of ink spreads through water, but never gathers itself back together, why heat flows from warm to cool and not the other way, why the universe as a whole moves always in one direction, toward greater mixing, greater uniformity, greater disorder. The second law does not merely describe what usually happens. It describes what always happens in every corner of the cosmos, without exception. A universe at maximum entropy can perform no thermodynamic work. There is simply no difference left anywhere from which energy could flow. Work, in the physical sense, requires a difference, a temperature gradient, a pressure difference, a concentration waiting to spread. When all such differences have been smoothed away, when the universe has reached its most evenly distributed state, nothing can drive any process forward. No engine can run, no reaction can proceed, no structure can form or change. The cosmos rests in a state of perfect, permanent balance, not empty exactly, but utterly without the capacity for anything new to happen. It is the universe at its most complete and its most still. In heat death, no gradients of temperature or energy remain anywhere in the universe to drive any process forward. Every difference that once existed between a blazing star and the cold void around it, between a warm planet and the dark space beyond, has been erased. The cosmos has become perfectly, uniformly flat in every thermodynamic sense. There is no slope left for energy to flow down, no imbalance left to resolve. The universe simply rests, complete and unchanging, in a stillness so total it has no inside or outside, no before or after. The heat death scenario is sometimes called the Big Freeze, a name that captures something of its quiet, unhurried nature. It is not a violent end, not a collapse or a tearing, but a slow, inexorable cooling, as if the universe were a vast breath being exhaled over trillions upon trillions upon trillions of years, until nothing remains but the faintest, most diffuse warmth, drifting toward absolute zero. The name is almost tender in its simplicity. A freeze, a settling. A universe grown so old and so spread out that it simply comes to rest. The Big Freeze is currently considered one of the most likely fates of the universe, given everything our observations tell us today. The evidence points toward a cosmos that will expand forever, growing colder and more diffuse with each passing era. It is a fate written not in fire or collapse, but in the slow, patient arithmetic of entropy. Scientists hold this conclusion with appropriate humility. Our understanding may yet deepen, but the weight of current evidence rests here, in this image of a universe drifting gently toward its longest, most enduring stillness. An alternative fate called the Big Rip could occur if dark energy does not remain constant, but instead grows stronger over time. In this scenario, the force driving the expansion of the universe does not merely hold steady, it intensifies epoch by epoch, becoming ever more dominant. Scientists refer to this hypothetical form of dark energy as phantom energy, a variety whose pressure would push outward with increasing ferocity. It is a possibility that current observations neither confirm nor rule out, a door that remains, for now, quietly open. In the Big Rip, the expansion of space accelerates without limit, growing faster and faster until the very fabric of the cosmos is stretched beyond all endurance. Every bound structure, every galaxy, every star, every atom finds itself pulled outward with a force that eventually overwhelms every other interaction in nature. Gravity, electromagnetism, the nuclear forces, one by one, they are overpowered by the relentless widening of space itself. The universe does not merely grow large, it grows without ceiling, without bound, until separation becomes the only remaining fact. The light reaching your eyes tonight from a distant star traveled for millions of years just to find you, and in the Big Rip, even that journey would become impossible. The Big Rip would unfold in a sequence, dismantling the universe layer by layer, from the largest structures down to the smallest. In the final billions of years before the end, the great clusters of galaxies that have held together across cosmic time would first be pulled apart, their gravitational bonds stretched beyond breaking. Then, individual galaxies would dissolve, their stars drifting free into an ever-widening void. Finally, solar systems, each one a delicate gravitational arrangement built over billions of years, would be scattered, their planets released into isolation. Eventually, the Big Rip would reach down to the smallest scales of reality. Planets would be torn apart, their rock and iron and ancient oceans flung outward into nothing. Stars would follow, their plasma unraveling, their nuclear fires extinguished not by exhaustion, but by the widening of the space within them. And then, in the final fractions of a second before the end, even atoms themselves would be torn open, their electrons stripped away, their nuclei shredded, the fundamental constituents of matter scattered into a universe that has finally grown too large for anything to hold together. Let yourself rest now, completely and without effort. There is nothing more to follow, nothing more to hold in mind. Feel the weight of your body, your shoulders, your hands, the length of your legs, all of it releasing downward, heavy and warm. Your breath moves on its own. You do not need to direct it. Simply notice the easy rise and fall, the natural rhythm that has carried you through every moment of your life without your asking. Let your thoughts thin out like mist over still water, each one drifting away before it fully forms. You are safe, you are unhurried, and sleep is very close now. The Big Rip, if it were to occur, would not take forever. It would happen in a finite span of time, estimated by scientists at tens of billions of years from now. This is an immense stretch by any human measure, and yet it is bounded, contained, a story with a last page. The universe would have a definite final moment, a specific instant beyond which nothing would remain. There is something almost clarifying about this, the idea that even the cosmos, in this telling, would have a natural end, arriving in its own time, unhurried and inevitable. The parameter governing, whether the Big Rip occurs, is called the phantom energy equation of state, a precise mathematical relationship that describes how the pressure and density of dark energy relate to each other. If this ratio crosses a particular threshold, the universe tips from a gentle, eternal expansion into the accelerating, boundless stretching of the Big Rip. Or scientists measure this parameter carefully, refining their estimates with each new observation of distant supernovae and the large-scale structure of the cosmos. For now, the value sits tantalizingly close to the boundary, not yet on one side or the other, and the universe keeps its final answer to itself. Current observations do not confirm phantom energy, but neither can they fully rule it out. The measurements scientists have gathered, from the faint light of distant supernovae, from the delicate patterns pressed into the cosmic microwave background, from the vast architecture of galaxy clusters, all of them sit close to the boundary, but none of them cross it decisively. The universe, for now, holds this question loosely, and there is a kind of ease in that, the knowledge that the answer is still open, still unfolding, still being written in the slow language of starlight and time. Another possible fate for the universe is known as the Big Crunch, a scenario in which gravity, rather than losing its hold on the cosmos, eventually reasserts itself and reverses the expansion entirely. In this telling, the outward drift of galaxies would slow, halt, and then turn around, drawing everything back toward everything else. The universe would begin a long, gradual homecoming, not a scattering, but a gathering. Like a breath drawn slowly inward after a long exhalation, all of space and matter would begin, over unimaginable stretches of time, to converge. In the Big Crunch, the universe would collapse back upon itself, folding inward, until all of space, all of matter, all of time compressed into a single point of infinite density. It is a mirror image of the Big Bang, not an explosion outward, but an implosion inward, arriving at the same kind of singular, boundless compression from which everything once emerged. Scientists call this a singularity, a place where the known equations of physics reach their limits and fall quiet. The universe, in this scenario, would end as it began, in a state beyond description, beyond measure, beyond anything our language was made to hold. The Big Crunch is considered unlikely given what we currently observe about the universe. The evidence, gathered over decades of careful measurement, points consistently toward an expansion that is not slowing but accelerating, driven onward by dark energy. For gravity to reverse this and pull everything back together, it would need to overcome a force that appears, for now, to be growing. Scientists do not dismiss the Big Crunch entirely, but they hold it gently as a possibility that the data has not favored. The universe, as best we can tell, is still moving outward and shows no signs of turning around. The Big Bounce theory offers a gentler reading of the Big Crunch, one in which the collapse does not end in permanent silence, but instead carries enough energy to rebound. In this vision, the universe falls inward to an extreme density, and then, rather than ceasing, springs outward again in a new Big Bang. The end becomes a beginning. The final compression becomes the seed of a new expansion. Scientists who explore this idea suggest that what we call the origin of our universe may itself have been a bounce, an echo of a previous cosmos that fell inward and was reborn. Cyclic cosmology takes this idea further, imagining not a single bounce but an endless series of them, universes expanding, contracting, rebounding, and expanding again across a span of time so vast it dissolves the very concept of a beginning or an end. In this framework, our universe is simply one chapter in an eternal story, one wave in an ocean that has always been rising and falling. Each cycle may last hundreds of billions of years, and yet the sequence itself has no first page and no last. There is something quietly comforting in this, the sense that existence itself may be not a single flame, but a rhythm. Mathematician and physicist Roger Penrose proposed a specific and elegant version of this idea, which he called conformal cyclic cosmology. In his model, the far future of one universe, grown cold, dark, and emptied of all massive particles, connects seamlessly to the Big Bang of the next. Penrose observed that a universe stripped of all mass loses its sense of scale entirely, and a universe at its very beginning, in the first instant of the Big Bang, also has no meaningful scale. These two extremes, he argued, are mathematically identical, and the ending and the beginning are in a precise sense the same moment. In Penrose's vision, the end of one aeon, his word for a complete cycle of cosmic existence, becomes the Big Bang of the next. The last photons of a dying universe, stretched to infinite wavelength and carrying almost no energy, pass through this boundary and emerge as the first light of a new creation. Nothing is lost, nothing is wasted. The universe does not simply end, it transforms, handing something forward across the threshold between one existence and the next. The light entering your eyes tonight may carry, in some unimaginably distant sense, the faintest inheritance of a cosmos that came before ours. Let yourself grow still now. There is no need to hold any of these ideas. Let them rest where they are, like stars resting in the sky. Feel the surface beneath you, solid and unhurried, supporting every part of you without effort. Your breath is slow and even. Your thoughts, if they come at all, are distant and soft, passing through without catching, dissolving before they fully arrive. You are here, you are warm, you are held. The vast and ancient universe continues its long journey far above and around you, and you are free to simply be still within it, drifting gently toward the deep and restful quiet of sleep. Vacuum decay is one of the more quietly astonishing scenarios physicists have imagined for the universe's fate, and it begins not with the stars or the galaxies, but with an invisible field that permeates all of space. The Higgs field, which gives particles their mass and underlies the structure of matter itself, may not be in its lowest possible energy state. Scientists describe this as a metastable condition, stable enough to have persisted for nearly 14 billion years, but not the most settled, most fundamental state the field could occupy. The universe, in this reading, may be resting in a valley that is not quite the lowest valley there is. The Higgs field permeates all of space and gives particles their mass. It is not something you can see or touch, yet it is present everywhere, woven through every cubic centimeter of the cosmos, from the heart of distant galaxies to the quiet air around you right now. Without it, particles would have no mass, matter would have no solidity, and nothing like a star or a world or a living thing could ever have taken shape. It is one of the deepest foundations beneath everything that exists. Physicists calculate that the Higgs field may be in a metastable false vacuum state. This means it is stable, remarkably, durably stable, but perhaps not in the most fundamental, lowest energy configuration it could occupy. Scientists describe it as sitting in a shallow valley on an energy landscape held in place by the shape of the terrain, but with a deeper valley somewhere further along that it has not yet found. The universe has rested here for nearly 14 billion years, undisturbed, like a stone that has never rolled. If the Higgs field were ever to tunnel to a lower energy true vacuum, a bubble of entirely new physics would begin expanding outward at the speed of light. It would start at a single point, smaller than an atom, and grow in a perfect sphere, carrying inside it a different set of physical laws, a different relationship between energy and matter. Everything the universe has built over billions of years, its stars, its atoms, its intricate chemistry, would lie in the path of that expanding boundary, waiting without knowing. A vacuum decay bubble would alter the fundamental laws of physics inside it, dissolving all structure as it passed. The forces that hold atoms together, the constants that govern chemistry, the relationships that make stars burn and planets orbit, all of these would shift into new configurations that bear no resemblance to the world we know. It is not destruction in the way we usually imagine it. It is more like a translation into a language that nothing in our universe was built to speak. Vacuum decay would be entirely undetectable and instantaneous for any observer in its path. There would be no warning, no light arriving ahead of it, no tremor in the fabric of space, no signal of any kind, because nothing can travel faster than the boundary itself. One moment, everything would be as it always has been, and then, in a way that admits no experience at all, it would simply be otherwise. Scientists note this not to unsettle, but because there is a strange, almost merciful stillness to it, a transition with no interval of knowing. Current measurements of the Higgs boson mass suggest the universe may indeed be in a metastable state. The precise value of the Higgs boson mass, combined with the mass of the top quark, places our universe in a region of the energy landscape that physicists describe as metastable, not quite stable forever, not quite unstable now. The numbers sit near a boundary, and scientists continue to refine them with each new experiment. The universe, it seems, may be balanced with extraordinary delicacy, like a dewdrop resting on the edge of a leaf at dawn. The time scale for vacuum decay, if it occurs at all, is estimated to be vastly longer than the current age of the universe. Scientists place it somewhere in the range of 10 to the power of several hundred years, a number so enormous it makes the current age of the cosmos feel like the first breath of a single morning. The universe has been here for nearly 14 billion years, and that span is, by this reckoning, barely a beginning. Whatever may or may not eventually unfold, it unfolds across a canvas of time so immense that all of human history is less than a whisper within it. The multiverse hypothesis suggests that our universe may be just one of countless bubbles within a far larger cosmos. In this picture, what we call the universe, all 160 billion or more observable galaxies, all of space and time as we know it, is a single bubble, one among an immeasurable number, each with its own history, its own physical laws, its own physical laws, its own arc from beginning to end. The scale of this idea is too vast to hold all at once, and perhaps that is fitting. Some ideas are best received not as thoughts to grasp, but as horizons to rest within. In eternal inflation, new universes constantly bubble off from an ever-expanding inflationary background. The underlying inflationary field, a vast, churning sea of energy, never stops expanding, and within it, pockets of lower energy continuously form and grow, each becoming a universe unto itself. Our own Big Bang, in this model, was one such pocket forming, one bubble rising and separating from the greater whole. The cosmos is not a single story with a single ending. It may be an endlessly branching garden, growing new existences in every direction, always and without ceasing. Let yourself settle now, a little more deeply than before. There is nothing to hold on to, nothing to work out, nothing to carry forward into this moment. Feel your breath moving slowly in and out, unhurried, effortless, as natural as the turning of the earth. Let your shoulders soften. Let your hands rest open. The ideas that have passed through this hour are vast and ancient, and they ask nothing of you now. They dissolve back into the dark like stars behind clouds, and what remains is only this: the warmth of the place where you are, the quiet around you, and the deep, unhurried drift toward sleep. Some multiverse models suggest that the end of our universe would be local rather than universal, a quiet conclusion to one chapter among countless others still unfolding. In this view, our universe might one day fade, collapse, or dissolve, while the greater multiverse continues on, indifferent and immense. Our ending would be no more than a single candle going out in a hall filled with an infinite number of flames. There is something oddly restful in that image, not loss, but proportion. String theory's landscape proposes that there exists an almost incomprehensibly vast number of possible vacuum states, each one a different set of physical laws, a different universe with different constants, different forces, different possibilities. Scientists estimate the number of such states may be 10 raised to the power of 500 or more, a figure that language can barely approach. Our universe, with its particular laws and its particular beauty, is one arrangement among an almost boundless library of arrangements. We happen to live in this one. The anthropic principle offers a gentle observation. Observers can only find themselves in universes that are compatible with the existence of observers. It sounds almost circular, and in a way it is, but it carries a quiet depth. The fact that you are here, breathing slowly in the dark, means that this universe, with all its precise and finely balanced constants, permitted you to exist. You are not incidental to the story. You are, in a very real sense, evidence that the story was possible at all. Boltzmann brains are a thought experiment, strange, dreamlike, and quietly humbling. The idea is this: in a universe old enough and large enough, random quantum fluctuations might, by pure chance, assemble a fully formed conscious observer from nothing, not through evolution or birth, but through the momentary, improbable ordering of particles. It is an idea that physicists take seriously, not because it is likely, but because it raises deep questions about the nature of mind, randomness, and what it means to exist at all. In a universe old enough, random fluctuations could theoretically reassemble any structure, not just a single mind, but an entire galaxy, a solar system, a world in bloom. Given enough time, the same arrangement of matter that formed the Milky Way could, by pure statistical chance, form again. The timescales involved are beyond all ordinary reckoning, but the mathematics permits it. The universe, in its deepest age, becomes something like a dreamer, capable of revisiting any form it has ever worn. The Poincaré recurrence theorem, developed by the French mathematician Henri Poincaré, states that any finite physical system will, given enough time, return to a state arbitrarily close to any previous state it has occupied. Everything that has ever been arranged, given boundless time, will be arranged again. It is a theorem of mathematics, cool and precise, and yet it carries within it something that feels almost like a lullaby, the idea that nothing is ever truly gone, only waiting, somewhere far ahead in time. A Poincaré recurrence for the observable universe would require a time scale so vast that no number we use in daily life, or even in astronomy, comes close to describing it. Scientists write it as 10 raised to the power of 10 raised to the power of 117, a tower of exponents that the mind cannot truly climb. It is not a number to understand, but to release, to let it drift past like a slow cloud, acknowledging only that time, in its fullest depth, is something far beyond what we have ever needed to imagine. The concept of the omega point, proposed by the physicist and theologian Frank Tipler drawing on earlier ideas, imagines all the matter and energy of the universe converging toward a final singularity of infinite complexity. In this vision, the end is not emptiness but fullness, a point where information and structure reach their ultimate density, where the universe folds entirely into itself. Whether or not this is physically possible, it is a remarkable image, the cosmos not dissolving into silence, but arriving at last at something complete. The physicist Freeman Dyson, writing with characteristic warmth and ingenuity, argued that life could persist forever in an open, ever-cooling universe, not by burning bright, but by slowing down, by reducing its metabolic rate in proportion to the falling temperature of the cosmos. A form of intelligence could, in principle, continue indefinitely. It would think more and more slowly as the universe aged, hibernating for longer and longer intervals between each thought, but it would never be extinguished. Dyson saw the universe as a place that, given creativity and patience, need never fall entirely silent. In Dyson's vision, an eternal intelligence would think ever more slowly as the eons deepened. Each thought stretched across millions, then billions, then trillions of years, but it would never reach the thought it could not finish. There would always be one more reflection, one more moment of awareness, however attenuated. It is a vision of mind as something fundamentally patient, willing to meet the universe on its own terms, however slow those terms become. And there is something soothing in that, the idea that awareness, like the universe itself, need not have an ending. Let your body settle a little more deeply now. Feel the weight of your limbs, the gentle rise and fall of your breath, the quiet warmth of wherever you are resting. There is nothing to hold on to tonight, nothing to figure out or remember. Let each thought loosen and drift away on its own, like leaves carried slowly downstream. You are safe, you are still, and all that remains is this soft and unhurried darkness cradling you toward sleep. Frank Tipler's omega point theory proposes that infinite computation occurs at the final cosmological singularity. In Tipler's vision, the collapsing end of the universe would not be a void, but a kind of ultimate processor. Every particle, every interaction, every thread of information woven together into something unbounded. It is a deeply unusual idea, blending physics with philosophy, imagining the last moment of time as a place of infinite richness rather than final silence. Whatever one makes of it, the image is quietly extraordinary. Most physicists consider Tipler's omega point physically implausible given the accelerating expansion of the universe. For the omega point to work, the cosmos would need to eventually halt its expansion and collapse inward, but everything we observe suggests the opposite is happening. The universe is not drawing together, it is spreading outward, growing ever more spacious. So the omega point remains a fascinating thought, held gently at arm's length by the evidence, a vision that physics has not confirmed, but that imagination finds difficult to fully release. The ultimate fate of the universe depends critically on the precise value of dark energy. Dark energy is not simply present or absent. It has a specific density, a particular strength, and the exact number that describes it will determine whether the cosmos drifts into stillness, tears itself apart, or follows some other path entirely. That single value, still not perfectly known, carries within it the entire future of everything. It is humbling to realize that one number, written somewhere in the fabric of space, holds so much. Observations from Type Ia supernovae first revealed that cosmic expansion is accelerating in 1998. Astronomers were studying these stellar explosions, remarkably consistent in brightness, useful as cosmic measuring sticks, and expected to find the expansion of the universe slowing down under gravity's pull. Instead, the distant supernovae were fainter than predicted, meaning they were farther away than they should have been. The universe was not decelerating, it was speeding up. That quiet discovery, made in the light of dying stars, changed our understanding of everything. Saul Perlmutter, Brian Schmidt, and Adam Riess were awarded the 2011 Nobel Prize in Physics for discovering the accelerating expansion of the universe. Working in two independent research teams, they arrived at the same astonishing conclusion from different directions, each confirming what the other had found. The prize recognized not just a discovery, but a transformation, a moment when the story of the cosmos had to be rewritten. It is a reminder that some of the most profound truths about the universe arrive quietly, encoded in the dimness of faraway lights. The cosmological constant, which physicists denote with the Greek letter lambda, is Einstein's term for the energy density of empty space. It represents the idea that a vacuum is not truly empty, that space itself carries a kind of intrinsic energy, pressing outward in every direction. Lambda is not a force in the familiar sense. It is a property woven into the geometry of the universe, present everywhere equally in every cubic centimeter of the void between galaxies. The emptiness of space, it turns out, is quietly full. Einstein originally introduced the cosmological constant to create a static universe, then later abandoned it. In the early 20th century, before observations confirmed that the universe was expanding, Einstein added lambda to his equations of general relativity as a kind of counterweight to gravity, a term that would hold the cosmos in balance. When Edwin Hubble's observations revealed that galaxies were receding, Einstein reportedly called the cosmological constant his greatest blunder. Decades later, it returned, not as an error, but as the key to understanding why the universe accelerates. The cosmological constant problem is the enormous discrepancy between the vacuum energy predicted by quantum field theory and the value actually observed in the universe. Quantum theory predicts that empty space should be seething with energy, an amount so vast it would have torn the universe apart almost instantly. Yet the observed value of lambda is extraordinarily small, almost vanishingly so. The gap between prediction and observation is among the largest in all of physics. It is a mystery held with patience rather than urgency, a quiet reminder that the deepest questions are still open. Future space telescopes will measure dark energy more precisely, helping to constrain the ultimate fate of the universe. Instruments not yet fully built will map the positions and distances of billions of galaxies across vast stretches of cosmic time, tracing the history of expansion with extraordinary care. Each new measurement will narrow the range of what is possible, drawing the universe's final chapter into slightly sharper focus. There is something deeply unhurried about that, humanity, patient and curious, slowly reading the last pages of a story that will not finish for longer than we can imagine. The James Webb Space Telescope is already refining measurements of the universe's expansion history, peering deeper into cosmic time than any instrument before it. Hovering nearly 1.5 million kilometers from Earth, it gathers ancient light with extraordinary precision, reading the universe's biography in the wavelengths of galaxies born when everything was young. Each observation quietly sharpens our picture of how expansion has changed across billions of years. The telescope does not rush. It simply listens patiently to a very old and very slow story. Let your body settle a little more deeply now. If you notice any tension still held in your shoulders, your jaw, the backs of your hands, simply allow it to soften and release. You do not need to hold anything right now. Let your breath move slowly, without effort, in and out, easy and natural. Your thoughts may drift like distant lights across a dark sky. You do not need to follow them. Just rest here, warm and still, as the universe continues its long, unhurried turning all around you. The Vera Rubin Observatory will map billions of galaxies to probe the nature of dark energy with remarkable thoroughness. Perched high in the Chilean Andes, it will survey the southern sky repeatedly over a decade, building an immense portrait of how the cosmos has grown and stretched across time. By tracing the positions and motions of billions of galaxies, it will help distinguish between the many possible forms dark energy might take. Each mapped galaxy is a quiet data point in one of the grandest questions humanity has ever asked. No current physical theory fully unifies quantum mechanics and general relativity. The two great pillars of modern physics remain, in a profound sense, unreconciled. Quantum mechanics governs the behavior of the very small with extraordinary precision, while general relativity describes the architecture of space and time on the largest scales. Yet when the two are brought together mathematically, they produce contradictions that neither can resolve. This is not a failure so much as an open door, a quiet invitation still waiting for someone to walk through it. A complete theory of quantum gravity might reveal entirely new physics governing the universe's ultimate fate. Such a theory would describe what happens at the smallest possible scales of space and time, where the fabric of reality itself becomes grainy and uncertain. It might show us that the universe's ending is not what our current equations suggest, that the story bends in directions we have not yet imagined. Scientists hold this possibility with a kind of open, unhurried wonder, the way one holds a question that is beautiful simply by existing. The information paradox asks whether information is truly destroyed when black holes evaporate, and it has occupied physicists for decades with quiet, persistent fascination. According to quantum mechanics, information about the state of any system can never be permanently erased, only transformed. Yet when a black hole radiates away its mass and disappears, what becomes of all the information that fell inside it? The paradox does not demand an urgent answer. It sits at the edge of knowledge, like a still pool, reflecting the sky, waiting. Stephen Hawking later came to suggest that black holes might preserve information in subtle encoded correlations woven into the Hawking radiation they emit. Rather than information being erased forever, it might be carried outward in the faintest patterns of the radiation itself, scrambled almost beyond recognition, but present nonetheless. This was a remarkable softening of an earlier view, a willingness to follow the mathematics wherever it led. It is a reminder that even the deepest convictions in science are held with a kind of graceful openness, always ready to be gently revised. The holographic principle proposes that all the information contained within a volume of space is fully encoded on its surrounding boundary surface, much the way a two-dimensional hologram contains the information needed to project a three-dimensional image. This idea emerged from the study of black holes and has grown into one of the most thought-provoking frameworks in theoretical physics. It suggests that depth itself, the interior of things, may in some profound sense be a kind of projection. Reality, at its most fundamental, may be thinner and stranger than it appears. The page curve describes how information encoded in Hawking radiation is gradually released over a black hole's entire lifetime, tracing a specific arc from early to late. Named for the physicist Don Page, it suggests that information does not simply vanish, it leaks out slowly, encoded in the growing correlations between emitted particles. In the early stages of evaporation, the radiation appears random, but over immense timescales, a hidden order accumulates. It is a curve drawn across unimaginable spans of time, tracing a kind of cosmic memory, patient and precise. Whatever its ultimate fate, the universe will have existed, for a span of time finite or infinite, bounded or open, brief by some measures and incomprehensibly vast by others. It will have held within it stars and dust and oceans and thought. It will have contained this moment and every moment before it. There is something deeply settling in that, not a conclusion, but a completeness. The universe does not need to last forever to have been real and full and astonishing. And right now, in this small corner of it, you are resting, warm and held and here. In a universe at maximum entropy, the arrow of time itself may lose all meaning. Time as we experience it flows in one direction because entropy increases, because things move from order toward disorder, from hot toward cold. But in a universe where nothing changes, where no gradient remains to tip the scales one way or another, there is no before and no after. There is simply a stillness so complete that the very idea of sequence dissolves. It is not an ending so much as a kind of eternal, featureless rest, vast, undisturbed, and absolute. And beneath all of it, beneath every theory, every equation, every vast and patient unfolding, the deepest mystery remains. Why is there something rather than nothing at all? Science can trace the universe back to its earliest moments, can map its likely futures across spans of time beyond all imagining, can describe the forces that shaped it with extraordinary precision. But the question of why anything exists at all rests in a quieter place, beyond the reach of any instrument. It is not a question that demands an answer tonight. It is simply one to carry softly, like a lantern held in cupped hands, as you drift toward sleep. You have traveled a long way tonight, from the warm, familiar present, through the slow dimming of stars, through the long silences of a cooling cosmos, all the way to the edge of what can be known and the shore of what cannot. And through all of it, through every billion years and every fading light, you were here, small and brief and extraordinary. The universe held you in this moment, as it has held every moment that ever was. Let that be enough. Let it be more than enough. Close your eyes now. Rest deeply. Good night.